Indeed, we created this graph right here. Oh, wait a minute. So this is the spectrum on that. It's a linear relationship. And we got that. Yeah. Then we said, what is the relationship between the risk of P and the weight of equity? And we said, well, the risk of P is equal to, I forgot, what's the formula for that?
It is the risk of debt squared.
You need to know this. So the weight
Oh,
of,
wait, my bad.
weight of
Weight of equity times the risk of equity.
risk of equity
Squared plus the weight of debt times the risk of debt squared.
plus twice
The weight times
Covariance.
covariance. And then what do you do with,
square root of 1/2.
you take the square root. Yeah? And what is this covariance thing?
That is rho times the two risks.
Risk of equity, risk of debt, covariance, that, right? So essentially, we said this relationship is non-linear, but also depends on what value of correlation we actually pick. And so when we did this graph, this is the weight of equity. Sigma P, sigma D, sigma E. And we said, depending on the value of correlation, this graph takes a different shape, even though it starts from here, ends here, but the path it takes to go from one extreme to the other is totally different. If correlation is positive 1, you get that. If correlation is negative 1, you get that. And if correlation is anywhere between, you get something that starts from the beginning point, ends at the end, but is always below this one. So you might get something that looks like these. These. Or these. Almost. Yeah. So which correlation is lower? The continuous red line or the dotted red line? The dotted red line. The lower the correlation, the more risk can be reduced. So we said, this is something interesting because the first thing that comes to my mind is that if I want to have a portfolio with a specific level of risk, before I only have one option. There was one asset allocation that gave me whatever risk I selected. But if correlation is low, I can actually have two possible ways to mix assets that give me the same amount of risk. So then the next question is one mix better than the other? Risk-wise, they're identical, but in terms of returns, they might be different. In fact, if this is my target, and let's suppose that I'm dealing with this dotted line, I have two weights that produce this level of risk. Weight of equity 1, weight of equity 2. You agree with that? And even though in terms of risk, those two selections are identical, is one better than the other? Well, let's see. If I have a low weight of equity, suppose this is my weight of equity 1, this is my weight of equity 2. So they're not exact replicas, but they're in the same order, right? So it's close enough. What do I get here? What is that? The first asset allocation produces a lower return than the second asset allocation. Same risk, different returns. So which allocation is better? WE1 or WE2?
WE2.
WE2, okay. What else can we get from there? We said, well, there is a specific asset allocation that produces by far the lowest amount of risk. So we were able to figure it out. So we were able to identify the weight of equity that produces the minimum variance, right? The minimum risk, and how was that figured out? Weight of equity that produces the minimum variance is equal to like sigma d squared minus covariance, sigma d squared plus sigma e squared minus twice the covariance. Where covariance is defined like that. Is that right? Check with your notes, because I don't remember this thing. How do we derive it?
We went back to the original that equation up there with sigma p, and then we solved the WE.
So we took this equation right here. We said, well, if you take the derivative, that tells you the equation of the slope. If you set the equation equal to 0, you find where the slope is 0, which is going to be at the bottom, right? The bottom of the sigma, it changes direction. So use that, then solve for the weight, and that tells you the weight that produces the lowest point. So that was the process, and this is the outcome of that process. Yep. So then we said, all right, this whole thing is interesting, but our goal was to find the best portfolio for the investor. So then we said, remember, how does the investor think? The investor thinks in terms of expected returns and risk. And so if you look at investor preferences, and if you give me some hypothetical portfolios, Y and Z, if you have those possible portfolios, using different curves in this graph can tell you what portfolio would be preferred by the investor. Which one is the best portfolio for this guy between X, Y, and Z? Remember? This portfolio right here is the same as this one. What about this one? This one is compared to Y prime. This portfolio, Y, is worse than Y prime. Is that right? Why? Same risk, low return, so Y prime is better than Y. If Y prime is on this indifference curve, then Y prime is the same as X prime, is the same as X. And all those portfolios are better than Y. So X is better than Y. Yep. And what about Z? Well, Z is clearly below it. So this is the tool that we have to figure out what investors like. How can we make these? How can we use this to figure out what is the best asset allocation for the investor? Well, given that this is what the investor thinks, then we need to modify the graph that of ERP is a function of the weight of equity, and sigma p as a function of the weight of equity, so that you have ERP as a function of sigma p, like this graph. So how do we go from two graphs that live in this space to one that lives in this versus that space? We said just pick the endpoints, figure out the minimum variance portfolio, and calculate those values. So now you have 3 points, and this graph will look like this. You have sigma p, ERP, This is what happens if you invest only in debt. Yeah, so those are the characteristics of debt, they're given in the problem basically. And then if you invest only in equity, equity has higher risk, has higher expected returns. You get this point. Then once you calculate the minimum variance portfolio, which is, you can figure out the weights by using this. Once you calculate those weights, you plug them in here, and you plug them in here, and you get the value of lowest, the lowest risk, the value of returns that coincide with their lowest risk. So you get a point in here. So this is the minimum variance portfolio, minimum risk. And you know that you're dealing with, it's an asset allocation that as you change the weight of equity will take you from here, progressively here, passing to this point. So this graph is gonna look like this. Yeah. So what this graph is telling us is that I can mix the weights between equity and debt in any possible way, and I can create portfolios that have characteristics of returns and risk that are matched along this line, along this curve. So like, can I get a combination of risks returns that are in here? Can I get that? No, because if I want this level of risk, sorry, if I want this level of returns, I can only get that level of return associated with this level of risk. I cannot get this return but higher risk, it's impossible. The only way I can combine those two things will generate combinations of risks returns depicted by the purple curve. Yeah? So remember, this is coming from here. Picture calculating for every weight, you calculate the yield risk, you calculate the return, and then you plot it in here. That's pretty much the way this is done. So this is what you're doing in project 2. You're not doing it for too risky assets, you're just doing it for risk-free and the risky asset, but the process will be the same. Questions? So this is telling us the feasible set of assets E and D. And those are all the possible combinations of risks and returns that you can create by mixing those two things. Yeah? So what should you be able to tell me from this graph? If this is my portfolio Q, I have this portfolio Q because I want this risk for some reason. I'm your client and I tell you, hey, I want that level of risk and nothing more. Am I selecting an ideal combination there or not? Or is there a better portfolio with that level of risk?
That level of risk is a better portfolio.
So if I want this level of risk, there is this portfolio that produces that, there is this other one right here, Q prime, that produces the exact same level of risk. But is one better than the other?
Yes,
Which one?
the one with the higher return.
The one with the higher return, right? So if I want to be exposed to this much risk, I have two options. One of the two is better because it has more potential for rewards. Yep.
So how is Q different from Q prime, besides that Q prime has more returns?
So the way how do you build it?
Or, so why, what would Q look like as opposed to Q prime? Like, how would an investor,
How would you go from one to the other?
yeah, like.
So let's work it out backwards. So suppose this is the amount of risk I want, right? And suppose I've constructed this graph. So if I want that level of risk, let me redo it because it's getting messy here. So, weight of equity, expected return over P. Weight of equity, sigma D. So now from this level, I get all the way to that level. The lowest amount of risk I get is this much. So lowest, highest, sorry, D, E, lowest is somewhere around here. One, so you start from here, and you get there. Do you agree with that so far? So, the moment I say I want to have a level of risk that is between the risk of D and the minimum risk, I'm saying that I want a level of risk that is below sigma D and minimum variance. So maybe Q is this much risk. This could be sigma Q. So I have Q and maybe Q prime on the two. So two different ways to create those portfolio with that level of risk. One way would have this weight of equity, let's call it weight of equity 1. This is gonna be obtained with a weight of equity 2. In correspondence with this weight, I also have this expected return and this expected return. So one of the two is gonna be Q, the other one is gonna be Q prime. Which one is Q? Well, Q is the one that has lower expected return than Q prime, same level of risk. So lower expected return than Q prime. This is gonna be lower expected return of Q. This is gonna be Q prime.
So that graph right on the left is like those two.
So this graph is obtained by, you create this by using the formula.
Okay.
And plotting points one at a time. Now for every weight, you pick one weight produces an expected return, and the exact same weight produces a risk. So now you have a pair. One weight creates one specific level of returns, one level of risk. Yep. So then you take these as a pair, like X coordinate, Y coordinate, and you get one here. So you're using those to construct that. Okay. The only reason we're doing this is because the way we define utility and indifference curves is in terms of expected returns of risk. But the way it's intuitive to build those portfolios is in terms of weight. Because as an investor, weight is the only thing that you can control. You decide how much to invest, right? So this is more intuitive. Then there is that pain of translating that into this.
Okay, that's what I was.
Okay. So okay, how does the investor pick a portfolio, you said? So I'm gonna replicate that because I messed it up with all the scribbles there. Sigma P, yeah, P. This is the smallest minimum variance portfolio, the one that has the smallest amount of risk. Now we take the investor preferences, and the investor will have those indifference curves here. And for this particular guy, which portfolio is best?
The one that touches the very end.
Is the one that is associated with the highest indifference curve. So this portfolio is feasible. This is also feasible. they can get that. What about this portfolio right here?
Not feasible.
Can you get this portfolio star? Why not?
It doesn't match the associated level.
It's not on the feasible set. The feasible set of portfolios is only the combination of these returns depicted by that curve. Anything off the curve is not possible. There is no way you can mix DNA and get a combination of these returns that is off the curve. So those are impossible. Those below here are impossible. The only thing that is possible is this path. Yep.
Is that top one not, that top one's not touching the line, right?
Yeah, I do it awful. So it should touch,
So it's supposed to touch just a small bit, right?
just tangent to it.
If it's touching it, then why is that not the optimal one?
So, hold on, this is feasible, is this feasible? It's just touching it a tiny bit. It is feasible.
Right, yeah, so
Yeah.
that would be the optimal one, cause that's
So-
the highest one there.
So out of this portfolio, and any other that is feasible, this is the best one.
Okay,
Why?
cause it's the one they prefer the most.
Because it's the one that is on the highest indifference curve. There is no way to touch this thing with indifference curves that are higher than that. Any curve above this one would not be touching the feasible set. Yeah? So, we call these the optimal risky portfolio. Optimal risky portfolio. So what are the four important portfolios in this graph? What are the four important points?
All points in the bottom.
So the one is when my portfolio P is identical to D. So I'm only investing in bonds and nothing else. This one is when I invest only in equity and no debt. What else?
The lowest risk one.
To me, the one that is important is this right here, what is the lowest level of risk, the portfolio with the lowest level of risk. And then measure utility.
Expected return
It's
minus
expected
one.
return that makes me happy, but then there is the risk that makes me unhappy. Do you agree with that? So, for portfolio P, for the portfolio that is a combination of E and D, can we figure out what the expected return is given the weights? Well, this expected return of P is the weight of equity, expected return of equity, minus, plus 1 minus the weight of equity. Expected return of debt. Do you agree with that? Where did I get this thing from? 1 minus weight of equity. This is the weight of debt. Yeah, okay. What about risk? Well, sigma P, here I'm looking for sigma squared, so let's directly get sigma P squared instead of taking the root. So this is the same as the weight of equity, risk of equity, squared plus 1 minus the weight of equity, squared, sigma T squared plus twice weight of equity, 1 minus the weight of equity, covariance. Do you agree with that? So, I know how to calculate this guy. So, picture substituting, let's call this number 1, let's call this number 2. So the way you can calculate utility as a function of weight is put equation number 1 here, minus 1/2 A, equation number 2 there. So I'm just substituting. So now this is giving me a relationship between the utility and the weight of equity given, sigma D, here D, sigma E, here E. And A. Those are all the pieces of information that are given in the problem. So the only thing that is variable is this weight of equity. So if you have a function and you want to find its max or min, what do you do? You take its derivative, set it equal to 0, and then so for whatever variable you are interested in changing. So this is the process that we should be doing. So to find the weight of equity that produces U max, what is that? Yeah, U max. Take the derivative. The derivative of U set equal to 0. And so for W. We're not gonna do it because I don't wanna spend half an hour taking derivatives and doing algebra, but this is pretty much the process. And when you do that, one hour later, you get for some reason here, I don't know why I solved it for WD. So here's what for WD, let me think about it. Here D minus here E. Obviously I don't expect you to memorize this thing. In the exam this formula will be given to you. Give me a second to write it and then double check it, and then you can copy it. Okay, so it's D, E, negative, positive, A, E. Yes, it's right. So let me figure out this other one. This is just swap. This one, yes. Okay, so you can solve for one or the other. got it? So what does this formula tell us?
Tells us the optimal point based upon the utility, for maximizing the utility or the satisfaction with those constraints.
Too complicated. Simple words.
Way to dead, way to equity.
To do what?
Define the ORP.
So if I want to construct the best possible portfolio and I wanna know how, what blend I need to have, this formula will tell me that. So all I need to know is what assets are you mixing together, the characteristics of the two assets, E and D. So expected return on E, expected return on D, risk on D, risk on E. The characteristics of the investor, okay, puts all these things together and spits out what is the best possible way to mix E and D so that the investor is gonna be as happy as possible. Yep? Questions? So let's try example. Consider the following two assets. So this is a table, and we have the expected return of E, 10%, 25%, 8, and 10. And the correlation, D and E, is -0.5. And the question is, plot the expected return of P. How much time do we have?
15 minutes?
15
No,
minutes.
20.
20 minutes, okay, so we should be able to do it.
Just
Yeah.
about.
Now, the expected return of P versus the weight of equity, risk of P versus the weight of equity. Compute the weight that generates the minimum variance portfolio. Compute the expected return and risk of the minimum variance portfolio. Then compute the weight of equity for the optimal portfolio. For an investor with we're not gonna finish it, but the follow-up question will be, what are the expected return and risk of the ORP of this investor? And then last, plot expected return of P against the risk of P to scale. So we need to calculate basically everything there is to calculate here. Questions? So, compute the weight of equity that generates the minimum variance portfolio. So which formula should we use? It's on the board. The one that gives you the smallest risk. What color is that formula?
Blue.
It's the one in blue, right? This one here. So let's think about this. This is using the risk squared and it's using covariance, right? So those are the two inputs in this calculation right here. Then it says use those weights to calculate the risk. But the formula for risk uses essentially the variance and the covariance. Do you agree with that? Of the two assets. And then finally the monster that we just derived uses the variance and the covariance. Do you agree with that? So if you want to do this problem in a relatively fast way, I would actually calculate in here sigma squared. So instead of recalculating these every time, I can just put the square value in the formula. So what is 25 squared is what, 625? Check my math. 625, then there is this single guy squared. And then 10 squared is 100. Single squared, yeah? So I just calculated that because I know it's going to be used in this formula. That way I don't have to recalculate it multiple times. I can just get it from here. And then the next thing that I need is the covariance. So let's calculate covariance. What is covariance? Is sigma D, sigma E, correlation D. So in here would be 25 times 10 times minus 0.5. So what is it, 122.5? Negative, do you agree with that? And the units are this symbol squared. Got it? So again, I'm doing this out of convenience so that when I do the calculations later, I don't have to recalculate stuff. So let's start with the plot of ERP against WE. So can you help me with numbers here? So WE and ERP. So if I invest everything in equity, what is my return?
Gonna be returned.
Everything in equity, my return is gonna be 15%. If I invest nothing in equity, what is my return? 10%. Do you agree with that? Questions? What about sigma P versus weight of equity? So if I try to graph this thing, if I invest only in debt, my risk is 10%. If I invest only in equity, my risk is 25. So start at 10, 25. This is only debt, this is only equity. Do you agree with those endpoints? The problem is that how is this graph going to look like? T and E are not connected by a straight line because correlation is some negative number. So the graph is going to be something like this. And to graph it precisely, I need to know how low this number is going to be, right? I need to figure out the location of the MVP. So in order to do this graph right here, I should do those two steps first. so that I can trace it precisely. So the way that generates the MVP. And so you take the formula right there is sigma D squared minus the covariance divided by sigma D squared plus sigma E squared minus twice the covariance. Did I copy right? Yep. So now I can put the values in it. And again, I calculated them earlier, so I don't have to do it. Sigma D is 100. The covariance is 122.5. Then you have 100 plus 6.5. 2. Yep. So you get 225, 2.5, this guy squared. And this is 2, is this number right? Yeah, it is right? Yep, you verified that?
I got 125 for that.
125,
Mm-hmm.
it didn't look right. I blame Ethan,
Oh.
because he said he was right. So, you're double fired. So this number is, sorry, replace it, 125. 125. So the math is easier now, it's still wrong. 225. And now that is 250, 875, 975, is that correct? Come on, use your calculator. Quick, quick, quick. I need to eat lunch. Is that right?
Yes.
Yep. So, what is the ratio? What do you got?
23.1%.
0.23, do you agree with that? Yes? So what does that number tell me?
That is the minimum, that's the weighted equity at the, minimum area.
So if I want to create a portfolio that has the smallest risk, I need to invest 23% in equity, and how much in debt? Well, 1 minus that 0.23, right? So that tells me the split. So the weight of that, the implication of this is that the weight of that, or the MVP, is 1 minus the weight of equity, or the MVP, 1 minus 0.23, 0.77, is that right? Yep. Alright, so now that I have the weight, I can calculate the expected return and risk, so that I can identify the risk here, and maybe I can place it here just for being a nerd. So what is the expected return of the MVP? What is the weight of equity, MVP, times ERE, plus the weight of debt, MVP, ERD. Okay, so what is the average of the expected returns? So this is 0.23 times, what's that guy? 15 and 8. What do you got? 9.61, 9.6, do you agree? Quick. We go with that? We trust Ethan again? Yeah, should be right. Anybody has verified that? What about risk? What is the rate of equity? Risk of equity? Rate of debt? Is that NPV? Rate of equity, NPV. Rate of debt, NPV. Covariance. Yep. Come on, we have 7 minutes to finish. So this guy is 0.23 squared. Sigma E squared, we calculated that earlier, is 625, so we can just plug it in there, so we don't need to square again. Then you have 0.77 squared times sigma D is 100 plus twice 0.23, 0.77. Covariance was negative 125. And then you take a nice square root at the end. Yep. Does anybody get the answer? You're actually using the financial calculator. Does anybody have a scientific calculator?
I don't know if
Mine
this
is
is.
dead.
Colby's got one.
Good, Colby.
I don't. I'm still writing. I'm still writing.
I absolutely refuse to do it.
Just barely loaded.
Writing MVP every time in subscript makes this extremely hard.
Well, okay, there we go.
Well,
Just say the weights are for MVP. That's it. With that calculator, it's gonna take a little while.
Yeah.
Did you get the answer, Bill?
I'll do it real quick.
I didn't.
I shall
finish
save you.
doing
Didn't
that
finish it.
second
Yeah,
thing.
you have to do it step by step. It's kind of an answer. Lesson learned, right? In the exam, what are you gonna use? The financial calculator or one that actually can do calculations?
Should I enter that as a decimal? The-
No, just leave it at 625. So remember, this is squared, whatever you get times this. This is squared, whatever you get times this.
Yeah, it's gonna be
Answer for it.
I did them as a decimal.
That's fine.
Okay.
It's just, it's annoying to do it in decimal because this is actually 625 divided by 100, whatever you get divided by 100 again. And then the answer that you get is gonna be a really tiny number. It's a bunch of zeros. And to me, it's more difficult. Every time I have a bunch of zeros, I forget one. And so my answer is messed up at the end.
Okay, is
So-
is the square on that just
It's all in this guy.
like to the percentage sign? I mean, in the 6.
This is just a symbol.
Okay.
Think of it as x squared. Yeah.
Whew.
you got it?
I got 145.
I don't.
145.
That
The
may.
answer should be less than 10.
What did I do
got
wrong?
6.9%, but yeah.
6.9%.
Scientific calculator didn't help me any.
So, all right, let's just
That'd be
write
easier.
6.9% and then we'll check the math.
How do you scroll?
Huh? With the arrow keys, brother.
Yeah, no, it's not. Go to the right.
Huh?
It's not letting me see the rest of the formula.
Put it in.
That's
And
fine.
what did you get? 6.9%?
9.
Yep. So, can we now draw this thing?
Yeah.
Well, the weight of the minimum variance portfolio is actually at 0.23. So 0.23 is about a quarter. So the lowest point is going to be here. How low is that point? It's 6.9%, provided you were correct. So an accurate drawing of this thing is something that starts here, ends there, passes through this point. Yep. And at a weight of 0.23, corresponds to a return of 9.6%. So if you want to create a portfolio that has by far the smallest level of risk, you need to mix this ratio. The risk you're gonna have is 6.9, but if you want this risk, you'll be exposed only to this return. Okay? Now, is this good for the investor? Well, it depends on here. So let's quickly calculate this weight of equity here. So optimal portfolio.
All right.
So what now?
My
For
picture.
the particular guy, is weight of equity is equal to the expected return of E minus ERD plus, which one am I copying? The one at the bottom, okay. A sigma D minus copy. Then the A sigma D sigma E minus copy. Yep. So let's put numbers in there and real fast. So this one I would do it in decimal form because I don't remember how the units of A are calculated. So the expected return of E is 0.15 minus 0.08 plus A is 10 for this guy. Sigma D is 100, so it's 0.1 squared is 0.01. Do you agree with that? Covariance is 125. Divided by 100 is 1.25. Divided by 100 again is 0.0125. Check it because I can't deal with zeros. Whatever. So it's minus 0.015. Then this one is again 10. Sigma D is 100 divided by 100 divided by 100 is 0.01 plus 625 divided by 100 is 6.25, so it's 0.0625 minus twice minus 0.015.
Should get that one now.
So
Fantastic.
quickly, what do we get? So what should we get? Well, we're not gonna get any less than, we shouldn't get anything less than 0.23, right? Because any optimal portfolio is gonna be between these two.
I got 0.3.
0.3,
I got 0.32.
0.3 even,
No. 0.302.
302, alright, so let's dump it like that. Yep. So we don't have time. We got all the way up to here. Okay, so how should we do those parts right here?
does that mean?
to find the actual risk and return of that portfolio. But once you have the weight, calculate that, and then, once you have all those points, then you can do the rest of the plot. Okay, so we're gonna finish it up on, Monday.
What does that mean?
This is the second to hardest